Example 4.1.5, a 2400 240 volt 60 Hz distribution transformer has a primary impedance of 0.72 plus J 0.92 ohms and a secondary impedance of 0.0070 plus J 0.0090 ohms. The impedance of the shunt branch is 632 plus J 4370 ohms. Draw and label the practical transformer model. So this example 4.1.5 introduces a lot of new terminology related to actual transformers. There is no such thing as an ideal transformer, and so to analyze actual transformers, what we do is we modify the ideal transformer model with some additional parameters that represent the actual behavior of the transformer in terms of passive circuit elements. So a big part of this is just knowing what the terminology is, and so I'll do that in the givens. We were given that it's a 2400 to 240 volt transformer, so that's nothing new. That's just the turns ratio. NP to NS is equal to 2400 divided by 240. So the 10 to 1 transformer, 10 to 1 step down transformer. We were told that it's 60 hertz, so the electrical frequency that these parameters are measured at is at 60 hertz. That's important because the parameters are given in terms of reactance, not inductance, so we need to know what the frequency is so that we are sure that they're applied at the correct frequency. But now we get into the actual parameters that modify the ideal transformer. The first are related to the primary, the series branch of the primary. There are two. There is the primary resistance and the primary leakage reactance. The symbol for the primary resistance is R1, and it was given to us as 0.72 ohms. And the primary leakage reactance is 0.92, and its symbol is XL1. So that's J 0.92 ohms. A lot of times those are combined together and to ZP, the primary impedance. We were then told that there's a secondary impedance. The symbol for secondary impedance can be divided again into two parts. The first is secondary resistance, that's called R2, and the second is secondary leakage reactance, that's XL2. So those are given to us as 0.0070 ohms and J 0.0090 ohms, and those can also be combined together. A lot of times they're called capital ZS, the impedance of the secondary of the transformer. Finally, we were given the impedance of the shunt branch. This has to do with these parameters here have to do with the physical characteristics of the fact that the transformers are made of coils of wire. So this represents the fact that it's a coil. This represents that it's made of wire. These terms, the shunt branch, however, has to do, I won't go into too much detail, but it has to do with the losses due to actually magnetizing the primary side of the transformer. Those are called the core loss resistance, given the symbol R sub C, and the inductive magnetizing reactance, and it's given the symbol X sub L M. Some books just call it X sub M, and that's J 4370 ohms. So those are the properties that we have to take into account when we're dealing with a practical transformer. So we're just asked to draw the, you know what, I'll just do it to the side for this example. We just need to find the practical transformer model. Practical. And I'm going to introduce a new piece of terminology here just for fun. A lot of times transformers are called X-formers. Practical transformer model. So the solution is you just kind of got to know what the practical transformer model looks like. It starts with an ideal transformer. modify from there. On the primary side, we have a series branch and we have a shunt branch. So the modification looks like this. We've got R2 as series and XL2 as series. And then we've got RC and XLM in shunt. So that's like that and like that. So that's RC and that's XM. On the secondary, we just have the secondary resistance and the secondary leakage reactance. Those are series elements. And so it looks like this. Oh, I labeled these incorrectly. That's X1 and XL1. Sorry, R1 and XL1. This is R2 and XL2. 2 is associated with the secondary, 1 is associated with the primary. So that's most of the practical transformer model. We just have to remember that these are the actual input terminals to the transformer, so the primary voltage appears here. This current through R1 and X1 is considered the primary current. The actual output terminals of the transformer are the secondary terminals. Those occur right here. And there's only one branch here, so that is I secondary. A lot of times this is called VS prime and this is called VP prime. They're not equal because of these series elements. VS prime does not equal VS. VP does not equal VP prime, right? The turns ratio, VS prime does equal VP prime through the turns ratio NP over NS right here. So these quantities are now what's relatable via the turns ratio, not VS to VP. So VP prime over VS prime is NP over NS. So this equation now holds. We also have a problem relating the primary current to the secondary current because there is a little bit of primary current. There is some current flow that flows through RL and X sub M that does not flow through the coil VP. So if we include these two, IP cannot be related to IS through the inverse turns ratio like we have done for the ideal transformer. So you can't do that relationship if you're including the effects of these. If, which is very common, you ignore these two, then IP flows through this coil and IS flows through this coil, and you can relate them, but only in the case where these are, where you're able to ignore those. In this class, we'll always ignore these quantities, and IP and IS are relatable via the inverse turns ratio. But in some other examples you may seek out or look up, or maybe you have a textbook you use or something like that, it's not necessarily the case because they may be including the effects of RL and X sub M. But anyway, that's the practical transformer model. It always looks like this. Just what happens is these different values change according to those.